All right, it's time to add a moon to our system. I'm going to do that by creating the object first. So we'll go right under Earth. We'll create a moon. It's going to be a sphere as well. We'll put it at a position equal to, the moon's pretty far from the Earth. If you Google things, you can find out it's about 384 million meters, 384 10 to the 6th away from the Earth. I'm going to set that just to the right in the x direction, kind of arbitrarily. The moon has a radius of 1.74 times 10 to the 6 meters, also Googleable, and a mass of about 7.3 times 10 to the 22 kilograms. Okay. So we've created that. Now if we run the program, we won't see the moon because it's way over here somewhere. It's just too far to see, so we'll have to adjust our viewpoint. I'm going to bump it out by about a factor of 10. Sorry, I'm trying to change the range right here. So we can see 10 times as far in every direction. And there's the moon. You can see it right there. Oh, if we scoot over, well, it's there. But it's kind of off-center. So I'd like to scoot the scene over so that we're centered right in the middle of our system between the Earth and the moon. I can do that by adding a center attribute to the scene, and that's going to be a vector again. And the vector just specifies the location of the center. I'm going to put it at the distance to the moon divided by 2, so halfway to the moon, and then 0, 0 in the other dimensions. Okay, that's pretty nice. Now our craft is still running into the Earth. Things are looking kind of small. It's a little hard to see. We can maybe we'll zoom this in just a little bit so we can see things a touch closer. And that's feeling pretty nice for now. Okay, the craft is still crashing into the Earth. The moon is not doing anything right now. It's just sitting out there in space. So we need to add gravitational forces between the moon and the craft. Here are the forces between the Earth and the craft. So we'll need to add a new line, and this would be F-grav from the moon. Now, way too awkward to have two things called F-grav. The program would just overwrite the previous one, and that's not cool. So I'm going to specify this is F-grav moon. Now, if I'm going to do that, I should go back and clean up other things. This was F-grav for the Earth right here, which means that, let's see, it used the radius of between the Earth and the craft, the Earth-craft distance right there. Let me just clean that up. Everywhere that shows up, I would need Earth-craft. You never think you're going to go back and look at your code later, but you will someday. And it's really helpful to have these notes to yourself. Okay, so now the moon force is going to look really similar. It's going to be that universal constant g again. It's going to depend on the craft mass and the moon mass. It's going to be divided by a distance again, but not the distance between the Earth and the craft. It needs to be the distance between the moon and the craft. So we'll make a new variable, and that's going to be moon position minus craft position. Okay, I can call that down here now that I've defined it. Mooncraft, square it, and then multiply it by the norm of the vector that points from the moon, from the craft to the moon. Okay. All right, let's see what happens. Actually, I see an issue, but we'll see what happens. R is not defined. Where do we leave an R in our code? Let's check that out. Where did we leave an R in our code? Here it is, crash condition. Okay, so we need this to be our Earthcraft. This is the Earthcraft condition. If we want to add a condition for the moon, we can do that later, and it would be something that looks very similar. F-grav is not defined. Down here we define the gravitational force of the Earth on the craft, of the moon on the craft, and then we need to add those two together. So this needs to be F-craft Earth plus F-grav moon, and those together make the net force on the craft. Then we're calling F-net divided by craft mass, and I think we're going to be okay in this case. Yep. Now the moon's still pretty far away, so it's not having any significant gravitational influence on that craft, which is very close to the Earth, and so we're not seeing it change the physics. I do want to launch the craft towards the moon, get it close enough so we can actually see if our new moon force is doing anything useful. To do that, I'm going to locate the craft just above the Earth. I'm going to put it at a Y position of twice the Earth radius, X position of 0, Z position of 0, so just above the Earth. And then I do need to give it some significant velocity. Now, this takes a bit of experimentation. I have done some experimentation with this, and I found that through trial and error, these numbers are pretty good. They should launch the craft out there and get somewhat close to the moon. There we go. We are on our way. I'm noticing I don't see our force vector, so I might boost that a little bit. I also notice the code's starting to run really slow and get jumpy. I think that's because these plots down here are getting larger and larger and larger, containing more values, and so we're running into a computation time issue. It does look like, if I can zoom in appropriately, over here there might be a little bit of influence from the moon. Let's speed things up first. Those plots are causing problems. I don't really need those plots right now. If I want to get data out, I could do that by creating plots later. That'd just take a little longer to run. Right now I'm going to comment out this plot so that it won't write those values to the plots at all. I'm also going to speed up the rate a little bit, though I think we're running into computation issues rather than rate issues. Okay, so now when I run the program, there we go. We have a pretty nice launch. We're getting close to the moon. It's taking a day of simulation time to get there. And then we do have a deflection right as we reach the moon's surface. Let me go just a little more time. Maybe we can do a day and a half. And I'm going to speed up the rate, the delta t. Not a whole lot's happening in a 100-second interval when we're on our way to the moon. So now we go quite a bit faster. You see that little bit of deflection right there as we approach the moon. I might be able to get a little bit closer. Let's see, this is the x velocity, the y velocity. Let me take down that y velocity by just a touch. I'll try 55 here. So it's not quite as far up. And you know, I think we want to do actually the opposite. We want to get a little bit closer to the moon. So we'll go with 3,700. There we go. Now we have a clear deflection as we've come very close to the moon. A couple things I want to do just to sort of play around with the visualizations, how this is showing up. I think that trail, that big white trail, is just a little bit heavy, so I'd like to reduce it. I can do that. Here's a little bit of syntax that'll do that for you. I can set the trail attribute of the craft, trail radius, to something smaller. There's a default value that depends on the scaling, where I'm setting it to 2 × 10⁵ meters, which sounds huge, but in the spatial scales that we're looking at, that's actually quite reasonable. Also, the craft looks really small. I have it with a radius of 0.3, which is essentially nothing on these scales. So I'm going to bump it up. Now, this is not, the shuttle would not be this large, but this just affects the visualization, so we can actually see the craft as it moves. And I'm not sure I could spot that, so let's go a little bit higher. Okay, this is starting to get ridiculously large. But now we can actually see it looks like a softball going through there, and that may be a bit too big. You can do what you like. It won't affect the physics. It will just affect the visualization, so you can see what's happening in your scenario.